There is something missing from the universe. Not missing in the way you might lose your keys or forget a name. Missing in a way that reshapes everything we thought we understood about existence itself. Missing in quantities so vast that all the stars, all the planets, all the gas clouds glowing in the depths of space, all the black holes, all the light we've ever seen or ever could see, all of it combined, accounts for less than 1/6 of the matter that must exist. The rest is dark, invisible, silent. It doesn't emit light. It doesn't absorb light. It doesn't reflect light. It passes through ordinary matter as though matter itself were nothing more than a suggestion. And yet without it, galaxies would fly apart. Stars would never have formed. You would not exist. This is the story of dark matter. How we discovered something we cannot see. How we mapped something we cannot touch. How we came to understand that the universe we know is merely the bright surface of something far stranger and far more vast. And how, after nearly a century of searching, we still haven't found it. If you enjoy exploring the hidden architecture of reality, consider subscribing. These deep investigations into cosmic mysteries arrive regularly, designed for curious minds who want to understand the universe as it actually is, not as we wish it to be. Let's begin where all good mysteries begin, with something that doesn't make sense. Imagine you're watching a carousel spin at a carnival. The horses near the center move slowly, taking small circular paths. The horses near the outer edge move faster, sweeping through wider circles to keep pace with the rotation. This is how spinning things work. The farther from the center, the faster the outer edge must travel to complete one rotation in the same time. This principle governs everything that spins. A spinning figure skater pulls their arms inward to spin faster, extends them outward to slow down. A spinning disc of pizza dough stretches wider as the outer edge whips around faster than the center. The planets in our solar system follow this same rule with remarkable precision. Mercury, closest to the Sun, races around its orbit at 47.9 kilometers per second. Earth, farther out, moves at 29.8 kilometers per second. Neptune, in the frozen outer reaches, crawls along at just 5.4 kilometers per second. This is not random. This is gravity. The Sun's gravitational pull weakens with distance, according to a precise mathematical relationship. Double the distance, and the gravitational force becomes 1/4 as strong. Triple the distance, and it becomes 1/9 as strong. This inverse square law means planets farther away feel less pull and orbit more slowly. The mathematics of this relationship were worked out by Johannes Kepler in the early 1600s, refined by Isaac Newton later that century, and confirmed by every observation since. It is one of the most fundamental, most reliable patterns in all of physics. So when astronomers in the 1930s began measuring how fast stars orbit within galaxies, they expected to see the same pattern. Stars near the galactic center should race around quickly, held in tight orbits by the concentrated mass of the galaxy's core. Stars farther out should move more slowly, their orbits languid and gentle, barely held by the weakening grip of distant gravity. Just like planets orbiting the sun, just like moons orbiting planets, just like everything else that orbits anything. That's what should have happened. That's not what they found. In 1933, a Swiss astronomer named Fritz Zwicky was studying the Coma cluster, a massive collection of over 1,000 galaxies, located roughly 320 million light-years from Earth, in the constellation Coma Berenices. Zwicky was not a patient man. He was brilliant, abrasive, intensely creative, and had a talent for seeing problems everyone else missed. He also had a talent for being dismissed by his colleagues, partly because of his difficult personality, partly because his ideas seemed too strange, too radical to take seriously. Zwicky was born in Varna, Bulgaria in 1898 to Swiss parents. His father was a businessman working abroad. Young Fritz was sent back to Switzerland for his education, where he studied physics and mathematics at the Swiss Federal Institute of Technology in Zurich, the same institution where Albert Einstein had studied 2 decades earlier. In 1925, Zwicky emigrated to the United States, taking a position at the California Institute of Technology in Pasadena, where he would spend the rest of his career. At Caltech, Zwicky became known for both his brilliance and his volcanic temperament. He had opinions about everything and expressed them with aggressive intensity. He feuded with colleagues. He felt his ideas were stolen and his contributions ignored. He called other astronomers spherical bastards, explaining that this meant they were bastards no matter which way you looked at them. He was not beloved, but he was undeniably talented. Zwicky coined the term supernova to describe exploding stars, distinguishing them from the less energetic nova. He proposed, years before any observational confirmation, that neutron stars should exist as the collapsed cause of supernova explosions. He developed innovative telescope designs. He had an instinct for looking at data that everyone else accepted as normal and seeing the one detail that revealed something profound. In the Coma cluster, he saw galaxies moving far too fast. Zwicky measured how fast individual galaxies were moving within the cluster using spectroscopy. When you look at light from a distant galaxy and spread it into a spectrum, you see dark absorption lines at specific wavelengths where elements in the galaxy's stars absorb light. These absorption lines act like fingerprints, identifying elements like hydrogen, helium, calcium, sodium. But the lines aren't quite where they should be. They're shifted, either toward the blue end of the spectrum or toward the red end. This is the Doppler effect, the same principle that makes an ambulance siren sound higher pitched as it approaches you and lower pitched as it moves away. Light from galaxies moving toward us gets compressed, shifted toward shorter wavelengths, toward blue. Light from galaxies moving away gets stretched, shifted toward longer wavelengths, toward red. By measuring how much the absorption lines shift, astronomers can calculate precisely how fast a galaxy is moving toward or away from us. Zwicky measured Doppler shifts for many galaxies in the Coma cluster. Some were moving toward us, some away, as they orbited within the cluster's gravitational well. From these measurements, he could calculate their velocities. The galaxies were moving at over 1,000 kilometers per second, relative to the cluster's center of mass. Some exceeded 1,500 kilometers per second. These speeds were shocking. Zwicky knew roughly how much visible matter the cluster contained. He could count the galaxies, estimate their masses from their brightness, add up the total. Using Newton's laws, he could calculate how fast galaxies should move in the gravitational field produced by that much mass. The answer was a few hundred kilometers per second, maybe 500, not 1,000, not 1,500. At the speeds Zwicky measured, the galaxies had enough kinetic energy to escape the cluster entirely. The cluster should have torn itself apart billions of years ago. The galaxies should have scattered into the void long before Earth even formed, before the Sun existed, before anything in our solar system condensed from the primordial cloud. And yet, there they were, the Coma cluster, stable, bound together, galaxies orbiting one another in a gravitational dance that had persisted for billions of years. Something was holding them together. Something with mass. Something with enormous gravitational pull. Something that Zwicky could not see. He called it Dunkel Materie, German for dark matter. Matter that doesn't shine. Matter that provides gravity but emits no light. Zwicky did the calculations. To hold the cluster together at the observed velocities, the total mass needed to be at least 400 times greater than the visible mass. 400 times. This wasn't a small correction, a subtle adjustment to make the numbers work. This was a complete reimagining of what the cluster contained, what the universe contained. If Zwicky was right, The stars and galaxies that filled telescopes, that seemed to constitute the entire cosmos, were merely a thin frosting on top of something vast and invisible. The universe was dominated by matter we couldn't see. Dark matter outweighed visible matter by a factor of hundreds to one. The astronomical community largely ignored him. Zwicky's measurements were difficult. The spectroscopy was challenging. The calculations involved assumptions about the cluster's geometry, about whether galaxies were orbiting randomly or in some organized pattern, about how long the cluster had existed. There were uncertainties, room for error, and the result seemed absurd. Invisible matter? Matter that emits no light? How could that be? Matter was atoms, and atoms interacted with light. They absorbed it, emitted it, reflected it. That's what made matter visible, what made astronomy possible. The idea that the cosmos might be dominated by something entirely different, something hidden, something that couldn't be seen no matter how powerful your telescope or how long your exposure, seemed like speculation, like fantasy, not science. Other astronomers proposed alternatives. Maybe Zwicky had miscounted the galaxies. Maybe there were many faint galaxies he'd missed, providing additional visible mass. Maybe the cluster wasn't really bound, and the galaxies were flying apart, and we just happened to see them before they dispersed. Maybe the velocity measurements were wrong. Zwicky grew increasingly frustrated and bitter. He felt his discoveries were dismissed unfairly, his brilliance unappreciated. He continued making important contributions to astronomy, discovering hundreds of supernovae, developing the wide-field Schmidt telescope, mentoring students. But his work on dark matter, perhaps his most important discovery, gathered dust in obscure journals, a curiosity, a possible error, something most astronomers simply didn't think about. For 4 decades, dark matter remained a footnote. Zwicky died in 1974, having never seen his discovery fully accepted. But Zwicky was right. And in the 1970s, a new generation of astronomers would prove it beyond any doubt. Vera Cooper Rubin was born in Philadelphia in 1928. As a child, she would lie awake at night in her bedroom, watching stars wheel across the window, wondering what they were and how they moved. Her father, an electrical engineer, encouraged her curiosity. Together, they built a simple telescope from a cardboard tube and lenses. Young Vera would spend hours observing the moon, planets, star fields. She wanted to study astronomy. This was not an easy path for a woman in the 1940s. Many universities didn't accept women into their science programs. Princeton's astronomy department flatly refused to consider female graduate students. Swarthmore College offered her a scholarship, but her heart was set on astronomy. So she attended Vassar College, one of the few institutions with a strong astronomy program that accepted women. At Vassar, Rubin thrived. She studied physics and astronomy, learned to use telescopes, began thinking about problems in galactic dynamics. She met Robert Rubin, a physical chemistry student, and they married. When she applied to graduate schools, Princeton rejected her without consideration. She enrolled instead at Cornell, where she could study with physicists who took her seriously. For her master's thesis at Cornell, Rubin studied the motions of galaxies on large scales, looking for evidence that galaxies had bulk motions beyond the simple expansion of the universe. Her results suggested galaxies might be rotating around some distant center, a controversial idea at the time. She presented her findings at a meeting of the American Astronomical Society. The reaction was skeptical, sometimes dismissive. Some astronomers questioned whether a woman could really understand the mathematics. Others simply didn't believe the results. Rubin persevered. She earned her doctorate from Georgetown University while raising 4 children, all of whom eventually became scientists. She took a position at the Carnegie Institution's Department of Terrestrial Magnetism, where she would spend the rest of her career. And in the early 1970s, she began the work that would transform cosmology. Rubin decided to study the rotation curves of spiral galaxies. Spiral galaxies are those elegant cosmic whirlpools, disk-shaped systems of stars and gas, rotating around a central bulge. Our own Milky Way is a spiral galaxy. Andromeda, the nearest large galaxy, is a spiral. They're common in the universe, and their rotation should follow predictable patterns based on the visible mass distribution. Rubin worked with Kent Ford, an astronomer and instrument builder, who had developed a highly sensitive spectrograph called the image tube spectrograph. This device could detect extremely faint light, allowing measurements of stars far from a galaxy's bright center. Together, Rubin and Ford began a systematic survey of spiral galaxies, measuring rotation velocities at many different distances from each galaxy's center. They started with Andromeda, the nearest major spiral, located about 2.5 million light-years away. Andromeda is visible to the naked eye as a faint smudge of light. Through telescopes, it resolves into a magnificent spiral, tilted at an angle that lets us see both its disk structure and its spiral arms. It spans roughly 3 degrees on the sky, about 6 times the width of the full moon, making it one of the largest apparent objects in the night sky. Rubin and Ford used telescopes at Kitt Peak National Observatory in Arizona, and later at Lowell Observatory, also in Arizona. They would spend long nights collecting spectra from different regions of Andromeda, measuring the Doppler shifts of stars and gas clouds at various distances from the galaxy's center. One side of Andromeda is rotating toward us, one side away. The rotation causes one side to show blue shifts, the other red shifts. By measuring these shifts carefully across the galaxy's disk, they could map the rotation velocity as a function of radius. They expected to see velocities peak near the center, where most of the visible mass concentrates, then decline farther out as the gravitational pull weakens. Just like planets orbiting the sun, just like everything else that orbits according to Newton's laws. Instead, they found velocities that stayed flat. Stars near the edge of Andromeda's visible disk were moving just as fast as stars closer to the center. In some regions, the velocity actually increased slightly with distance. The rotation curve didn't decline. It stayed flat, or even rose. This was impossible if visible matter was all that existed. The visible stars and gas peter out at large radii. The mass distribution drops off. Gravity should weaken. Orbital velocities should decline. They don't. Rubin checked her instruments carefully. She checked her data reduction procedures. She looked for systematic errors, for instrumental effects that might create false signals. Everything checked out. The flat rotation curve was real. She observed more galaxies, dozens of them. Then hundreds. Different types of spirals, different orientations, different sizes and masses, different distances from Earth. Every single one showed the same pattern. Flat rotation curves. Stars and gas at the outer edges, moving far too fast to be held in orbit by the gravity of visible matter alone. By the late 1970s, the evidence was overwhelming. Galaxy after galaxy, measurement after measurement, all pointed to the same conclusion. Galaxies contained far more mass than we could see. Mass that didn't glow. Mass that didn't emit light at any wavelength. Mass that could only be detected through its gravitational effects on the motion of stars and gas. Dark matter. This time, the scientific community couldn't ignore the evidence. Rubin's measurements were precise, systematic, reproducible. Other astronomers confirmed her findings using different telescopes, different techniques. Radio astronomers mapped the distribution of hydrogen gas in galaxies using the 21-centimeter emission line and found the same flat rotation curves extending even farther than optical measurements could reach. By the early 1980s, dark matter had transitioned from a curious anomaly to an established fact. The universe contained vast quantities of matter we could not see, matter that outweighed all the visible stars and gas by a factor of at least 5 to 1, possibly 10 to 1 or more. Everything we had ever seen through any telescope, every galaxy, every star, every glowing nebula, every planet, every comet, every grain of cosmic dust, all of it combined, made up less than 20% of the matter in the universe, perhaps less than 15%, perhaps even less than 10%. The rest was dark, invisible, unknown. Vera Rubin's work earned her numerous awards and honors. She became the second woman astronomer elected to the National Academy of Sciences. She received the National Medal of Science from President Bill Clinton. She was a leading candidate for the Nobel Prize, though the prize never came. Many in the astronomical community felt this was an injustice, a recognition denied for discoveries as fundamental as any in 20th century physics. Rubin died in December 2016 at the age of 88. But her legacy lives on. She proved that the universe we see is not the universe that exists. She showed us that reality extends far beyond the reach of light. She opened a door into a cosmos stranger and vaster than anyone had imagined. And through that door, physics stepped into one of the deepest mysteries it has ever confronted. Pause here for a moment. Let's absorb what we've learned so far. We know from direct observation that galaxies rotate in ways that don't make sense if visible matter is all that exists. We know this from two independent lines of evidence. Zwicky's measurements of galaxy clusters in the 1930s, showing galaxies moving too fast to be held by visible mass alone, and Rubin's rotation curve measurements in the 1970s, showing stars orbiting too fast at large distances from galactic centers. These aren't theoretical predictions. These aren't speculations or thought experiments. These are measurements, real data from real telescopes pointed at real galaxies. The observations are solid. The mystery is real. But observations tell you what, not why. They tell you that something unexpected is happening, but they don't automatically tell you what's causing it. When rotation curves stay flat instead of declining, there are fundamentally two possible explanations. First possibility: galaxies contain more matter than we can see. The visible stars and gas represent only a fraction of the total mass. The rest is dark, invisible, detectable only through gravity. This dark matter provides the additional gravitational pull needed to keep stars moving fast, even at large distances from the galactic center. Second possibility: our understanding of gravity is wrong. Maybe gravity doesn't weaken with distance in exactly the way Newton and Einstein described. Maybe at very large distances or very weak accelerations, gravity behaves differently, declining more slowly than expected. In that case, visible matter alone could produce enough gravitational pull to explain flat rotation curves without requiring any additional invisible mass. Both explanations are scientifically reasonable. Both are testable. And over the past 4 decades, physicists and astronomers have pursued both possibilities, trying to determine which explanation matches reality. The dark matter explanation requires us to accept that most of the universe is made of something we've never directly detected. This seems strange, perhaps even troubling. How can we claim to understand the universe if most of it is invisible? The modified gravity explanation requires us to accept that one of the most fundamental laws of physics, a law tested countless times in countless ways, breaks down under certain conditions. This also seems strange. Gravity has been studied for centuries. It works everywhere we can test it. Why would it suddenly work differently in galaxies? Strange versus strange, invisible matter versus modified physics. Which explanation is correct? The answer, as we'll explore, comes from looking beyond just galaxy rotation curves. When you examine many different types of observations across many different scales, one explanation consistently works better than the other. The evidence points in a clear direction, though not without some lingering questions and puzzles. But before we dive into that evidence, we need to understand what dark matter could be. What kind of matter doesn't interact with light? What properties must it have to match observations? And why is it so hard to detect? You are made of atoms: carbon, oxygen, hydrogen, calcium, phosphorus, iron, and trace amounts of many other elements. These atoms were forged in the nuclear furnaces of ancient stars that lived and died before the sun even formed. When those stars exploded as supernovae, they scattered their enriched material into space. That material, mixed with primordial hydrogen and helium, collapsed into new clouds, formed new stars and planets. Some of those atoms ended up on Earth. Some ended up in you. Every atom in your body has existed for billions of years, cycling through stars and gas clouds and planets, recycling endlessly. The calcium in your bones was created in a supernova explosion. The iron in your blood was forged in a dying star's core. You are quite literally made of stardust. This is not poetry. This is physics. This is your actual origin story, written in the periodic table. This type of matter, the matter you and I are made of, the matter that makes up stars and planets and galaxies, is called baryonic matter. The term comes from baryons, which are particles like protons and neutrons, the building blocks of atomic nuclei. When physicists and astronomers talk about ordinary matter, or normal matter, or baryonic matter, they mean the same thing. Matter made of atoms, matter composed of protons, neutrons, and electrons. The stuff of the periodic table, the stuff that interacts with electromagnetic radiation, that can be seen and touched and measured directly. Dark matter is not baryonic. It is something fundamentally different. We know this with certainty because baryonic matter, matter made of protons and neutrons, interacts with light in specific, unavoidable ways. All atoms contain charged particles. Protons carry positive charge. Electrons carry negative charge. These charges interact with electromagnetic fields, with photons, with light. When light shines on an atom, several things can happen. The atom might absorb a photon if the photon's energy matches the energy difference between electron orbitals. The electron jumps to a higher energy level, and the photon disappears, its energy absorbed. Later, the electron falls back down, emitting a new photon. This is why neon signs glow, and why gases in stars produce specific spectral lines. If the light doesn't match an absorption line, the atom might scatter the photon, deflecting it in a new direction. This is why clouds are white and why the sky is blue. Scattering redirects light without absorbing it, but it still involves electromagnetic interaction between photons and charged particles. Or the atom might simply ignore the photon if the energy is too low or too high to trigger any transition. But even then, the photon's electromagnetic field interacts infinitesimally with the atom's charged particles. The interaction exists just weakly. The point is that baryonic matter always interacts with electromagnetic radiation somehow. It has to. It contains charged particles, and charged particles coupled to electromagnetic fields. This is fundamental to quantum mechanics and quantum electrodynamics. There's no way around it. Dark matter doesn't interact with light. Not at all. Not weakly. Not rarely. Not in any detectable way whatsoever. You could shine 1,000,000,000 watts of laser light through a cloud of dark matter, and the light would pass straight through, completely unaffected. You could heat dark matter to 1,000,000,000 degrees and it wouldn't glow. You could compress it to extraordinary densities, and it wouldn't emit a single photon. This tells us dark matter cannot be made of atoms. It cannot contain electrically charged particles. It cannot be baryonic. There's another way we know dark matter isn't baryonic, and it comes from studying the very first moments after the Big Bang. In the beginning, there was light. Not metaphorical light, but actual light. Electromagnetic radiation at unimaginable energies and temperatures. The universe began in an extraordinarily hot, dense state, about 13.8 billion years ago. In the first tiny fractions of a second, the universe was far too hot for any particles as we know them to exist. Energy and matter were interchangeable, particles constantly being created and destroyed as photons collided with enough energy to produce matter-antimatter pairs. As the universe expanded, it cooled. After about 1 microsecond, it had cooled enough for quarks to bind together into protons and neutrons. These are still the same protons that exist in your body today. Protons don't decay. They're apparently stable over timescales far longer than the current age of the universe. The protons that formed 1 microsecond after the Big Bang are still around. For the next few minutes, the universe was hot enough for nuclear fusion to occur everywhere at once. Protons and neutrons collided and stuck together, forming the first atomic nuclei. Mostly they formed deuterium, which is heavy hydrogen with 1 proton and 1 neutron. Deuterium nuclei collided and fused into helium nuclei, which contained 2 protons and 2 neutrons. Some helium fused into lithium. Tiny amounts of beryllium formed. This period, called Big Bang nucleosynthesis, lasted only about 3 to 20 minutes. By 20 minutes after the Big Bang, the universe had cooled and expanded enough that nuclear fusion stopped. The density and temperature dropped below the threshold needed for nuclei to overcome their electromagnetic repulsion and fuse together. When nucleosynthesis ended, the universe contained a specific mixture of light elements, about 75% hydrogen, 25% helium by mass, and trace amounts of deuterium, helium-3, lithium, and beryllium. These ratios aren't random. They depend on the physics of nuclear fusion and on how many baryons, how many protons and neutrons existed during those crucial minutes. The key insight is this. The more baryons present, the more efficiently fusion proceeds, and the more helium gets produced relative to hydrogen. If the universe had contained more protons and neutrons, more collisions would have occurred, more deuterium would have fused into helium, and the final mixture would be helium-heavy. If it had contained fewer baryons, fusion would have been less efficient, and the final mixture would be more hydrogen-heavy. We can measure these primordial element ratios by observing ancient gas clouds that haven't been contaminated by stellar nucleosynthesis, that still contain the original mixture from the Big Bang. These observations are challenging because most gas has been cycled through stars, which fuse hydrogen into heavier elements and change the ratios. But a few pristine clouds remain, particularly clouds so diffuse they never collapse to form stars. By analyzing these clouds carefully, astronomers can measure the primordial abundances. The measurements match theoretical predictions beautifully, but only if the total amount of baryonic matter in the universe equals about 4 to 5% of the critical density needed to make the universe spatially flat. The critical density is a specific number derived from Einstein's equations of general relativity. It's the density where the universe's geometry is exactly balanced, neither positively curved like a sphere, nor negatively curved like a saddle. Observations show the universe is very close to flat, possibly exactly flat. This means the total density equals or very nearly equals the critical density. But only 4 to 5% of that density can be baryons. If more baryons existed, Big Bang nucleosynthesis would have produced the wrong element ratios. The predictions wouldn't match observations. The theory would fail. So we know precisely how much baryonic matter exists in the universe. About 4 to 5% of the critical density. This is ordinary matter. Atoms, protons and neutrons and electrons. Now, independent observations of galaxy rotation curves, of galaxy clusters, of gravitational lensing, of large-scale structure, all require total matter density around 25 to 30% of the critical density. far more than the 4 to 5% allowed for baryons. The difference between 30% total matter and 5% baryonic matter is dark matter. About 25% of the universe's density, about 85% of all matter, must be something other than atoms, something non-baryonic, something dark. This is airtight reasoning based on solid observations and well-tested physics. Dark matter cannot be ordinary atoms hiding in some dark form. It has to be something else, something that didn't participate in Big Bang nucleosynthesis, something that doesn't interact electromagnetically, something entirely new. But what? The search for an answer has consumed physics for half a century, and it begins with thinking carefully about what properties dark matter must have to match observations. First, dark matter must have mass. This seems obvious, but it's worth stating explicitly. Dark matter produces gravitational effects. Gravity comes from mass and energy. Dark matter has to have one or both. Since we don't see any associated energy, it must be mass. Dark matter particles, whatever they are, must be massive. Second, dark matter must be stable, or at least very long-lived. The dark matter halos around galaxies have existed for billions of years. If dark matter particles decayed quickly, the halos would evaporate and galaxies would fly apart. We don't see this happening. So, dark matter particles must either be completely stable, never decaying at all, or have lifetimes longer than the current age of the universe. Third, dark matter must be cold or at most warm. This terminology refers to particle velocities. Hot dark matter would be particles moving at speeds close to the speed of light, relativistic speeds. Warm dark matter would be particles moving at intermediate speeds, faster than typical galactic escape velocities, but slower than light. Cold dark matter would be particles moving slowly, compared to the speed of light, with velocities similar to or slower than stars in galaxies. Why does this matter? Because fast-moving particles don't clump together efficiently. They have too much kinetic energy. Their velocities carry them away from gravitational wells before they can settle down. Hot dark matter would have smoothed out structure in the early universe, making it hard to form galaxies when observations show they formed. Cold dark matter, moving slowly, can clump together efficiently, allowing structures to form early. Observations of large-scale structure, of when galaxies first appeared, of how matter is distributed on different scales, all favor cold dark matter. The universe's structure matches simulations of cold dark matter, gravitational collapse, much better than simulations using hot or warm dark matter. Fourth, dark matter must be electrically neutral. No electric charge. We know this because charged particles interact electromagnetically, and dark matter doesn't. No exceptions. Fifth, dark matter must not interact through the strong nuclear force. The strong force binds quarks into protons and neutrons, binds protons and neutrons into atomic nuclei. If dark matter felt the strong force, it would form dark matter nuclei, tightly bound clumps. The distribution of dark matter in galaxies doesn't look like that. It looks smooth and diffuse, like particles that don't bind together. So dark matter doesn't feel electromagnetism or the strong force. That leaves only gravity and possibly the weak nuclear force. Gravity definitely affects dark matter. We detect dark matter through gravity. That's the whole point. The weak nuclear force is more interesting. The weak force is responsible for certain types of radioactive decay, for fusion processes in the sun's core, for interactions involving neutrinos. It operates at extraordinarily short ranges, smaller than an atomic nucleus, but it affects certain classes of particles. If dark matter interacts through the weak force, it opens up a possible detection path. Weak force interactions are rare but not impossible. A dark matter particle interacting through the weak force might occasionally collide with an ordinary atomic nucleus, transferring a tiny amount of energy. With a sensitive enough detector, you might catch one of these incredibly rare events. This led to the most popular dark matter hypothesis, WIMPs, which stands for Weakly Interacting Massive Particles. The WIMP hypothesis emerged from particle physics in the 1980s and quickly became the leading candidate for dark matter. The appeal was both theoretical and observational. Theoretically, WIMPs arose naturally from extensions to the standard model of particle physics. The standard model, developed in the 1960s and 70s, describes all known fundamental particles and three of the four fundamental forces: electromagnetism, the strong nuclear force, and the weak nuclear force. It's been extraordinarily successful, making predictions confirmed to many decimal places of precision. But the standard model has gaps. It doesn't include gravity at the quantum level. It doesn't explain why neutrinos have mass, when early versions of the theory predicted they should be massless. It doesn't explain the huge difference in strength between the weak force and gravity, a puzzle called the hierarchy problem. It doesn't explain why the universe contains more matter than antimatter, when the Big Bang should have created equal amounts of both. To address these problems, physicists developed theoretical extensions beyond the standard model. One popular extension is supersymmetry, a mathematical framework that predicts every known particle has a heavier superpartner particle. Electrons have selectrons. Quarks have squarks. Photons have photinos. These superpartner particles would have different spins and masses, but otherwise similar properties to their standard model counterparts. Supersymmetry, if real, solves several problems in particle physics. It helps stabilize the Higgs boson mass, addressing the hierarchy problem. It provides candidates for unifying the fundamental forces at high energies. And crucially, it predicts stable massive particles that interact only through gravity and the weak force. These particles would be WIMPs. They would be dark matter candidates, naturally emerging from a theory developed for completely different reasons. The lightest supersymmetric particle, often called the LSP, should be stable if supersymmetry conserves something called R parity. This stability means LSPs produced in the early universe would still exist today, having never decayed. They would have mass typically predicted to be tens to thousands of times heavier than a proton. They would interact through the weak force, but not through electromagnetism or the strong force. They would be invisible. They would be exactly what dark matter needs to be. This seemed almost too good to be true. A theoretical framework developed to solve particle physics problems independently predicted particles with exactly the right properties to be dark matter. It felt like the universe was giving us a hint, pointing us toward the right answer. There was another piece of supporting evidence, something called the WIMP miracle. If WIMPs exist with masses and interaction strengths in the range supersymmetry predicted, calculations showed they would be produced in the right abundance during the Big Bang to account for observed dark matter density. This wasn't obvious. It required detailed calculations about particle physics in the early universe, about how WIMPs would be created and annihilated in the hot, dense plasma, about when they would freeze out and become stable relics. The calculation went like this. In the first microseconds after the Big Bang, the universe was hot enough that particles and antiparticles were constantly being created from pure energy and annihilating back into energy. As space expanded and cooled, the average energy dropped. Eventually, the universe cooled below the threshold needed to create heavy particles like WIMPs. At this point, WIMPs stopped being produced. But existing WIMPs could still annihilate with each other if they collided. The annihilation rate depended on the WIMP interaction strength. Stronger interactions meant more frequent collisions and more annihilation, leaving fewer WIMPs as relics. Weaker interactions meant less annihilation and more surviving WIMPs. For WIMPs with weak force interaction strengths and masses around 100 times the proton mass, the calculations predicted a relic density of about 20 to 30% of the critical density. This matched the observed dark matter density beautifully. This coincidence, that particles with weak force interaction strengths naturally produce the right amount of dark matter, became known as the WIMP miracle. It suggested we were on the right track. The same physics that governs radioactive decay and solar fusion might also govern dark matter. So physicists set out to detect WIMPs. If the hypothesis was correct, WIMPs should be everywhere. The Milky Way should be embedded in a vast halo of dark matter, and Earth, orbiting within that halo at about 220 kilometers per second, should be constantly bombarded by dark matter particles. How many? According to calculations, if dark matter consists of WIMPs with masses around 100 proton masses, roughly 100,000 WIMPs pass through every square centimeter of Earth every second, through your hand, through your head, through every atom of your body, billions upon billions constantly streaming through you, completely unnoticed. Most pass straight through without touching anything. The interaction probability is vanishingly small, but occasionally, maybe once in a trillion interactions, a WIMP might get unlucky and collide with an atomic nucleus. The nucleus would recoil, absorbing a tiny bit of energy from the collision. That recoil could be detected. This became the strategy. Build ultra-sensitive detectors and wait for the extremely rare WIMP collision. Detecting something that almost never interacts is one of the most difficult experimental challenges in physics. You're searching for a signal so rare that you might see one event per year per kilogram of detector material. Meanwhile, you're bombarded by background noise from cosmic rays, from natural radioactivity, from electronic fluctuations, all of which can mimic a dark matter signal. The first challenge is location. You need to go deep underground to shield against cosmic rays. Cosmic rays, mostly protons, accelerated to high energies by supernova shocks and other violent cosmic events, rain down on Earth constantly at about 100 particles per square meter per second at sea level. When these particles hit the atmosphere, they create cascades of secondary particles, pions, muons, electrons, photons. Some penetrate all the way to the ground. Muons in particular can pass through substantial amounts of matter. A muon passing through your detector looks very similar to a WIMP collision. Both deposit energy. Both create recoil signatures. The solution is shielding, and lots of it. Rock works well. Every meter of rock between your detector and the surface reduces the cosmic ray flux by absorbing and scattering particles. At around 1,500 to 2,000 meters underground, the muon flux drops to manageable levels, reduced by a factor of about 1,000,000 compared to the surface. This is why dark matter experiments occupy deep underground laboratories. The Homestake Mine in Lead, South Dakota, extending more than 1,400 meters below the surface. The Sudan Mine in Minnesota, over 700 meters deep. The Gran Sasso National Laboratory in Italy, built inside a highway tunnel through the Apennine Mountains, with about 1,400 meters of rock overhead. Snall B in Sudbury, Canada, over 2,000 meters underground, in an active nickel mine. The China Jinping Underground Laboratory, the deepest in the world, beneath about 2,400 meters of rock. These laboratories required massive infrastructure investments. You need elevators capable of descending thousands of meters, climate control to manage temperature and humidity in an environment that would otherwise be hot and humid from geothermal heating, clean rooms to assemble sensitive detectors in particle-free environments, power supplies, data acquisition systems, safety equipment. Building a physics laboratory deep underground costs far more than building one on the surface. But there's no alternative. You need the shielding. Even underground, backgrounds remain. Natural radioactivity is everywhere. Uranium and thorium exist in trace amounts in rock, decaying slowly and releasing alpha particles, beta particles, and gamma rays. These decay products can reach your detector. Radon gas, a radioactive decay product of uranium, seeps from rocks and can contaminate detector volumes. Even cosmic ray muons occasionally penetrate thousands of meters of rock, and when they do, they can create showers of secondary particles in the detector itself. Every component of the detector must be screened for radioactive contamination. The metal used for detector housings and shields, the photomultiplier tubes that detect light signals, the wires and cables, the electronic components, everything. Even the solder used to join components together can contain radioactive isotopes if not sourced carefully. Physicists source ultra-pure materials from specialized suppliers. They use ancient lead salvaged from Roman shipwrecks, lead that has been underwater for 2,000 years, long enough for short-lived radioactive isotopes like lead-210 to decay away to undetectable levels. They use copper mined from deep underground veins that haven't been exposed to cosmic rays, which can activate copper and create radioactive isotopes. They clean all surfaces meticulously to remove dust and contaminants. The detector itself must be designed to distinguish a genuine WIMP collision from background events. Different detector technologies have been developed, each with different strengths. Liquid xenon detectors are currently the most sensitive. These consist of large tanks filled with ultra-pure xenon, cooled to -95 degrees Celsius, cold enough to liquefy it. Xenon is chosen because it's a heavy element with a large nucleus, providing a substantial target for WIMPs to hit. It's also chemically inert, doesn't react with container materials, and produces good signals when particles interact with it. When a particle strikes a xenon nucleus, the nucleus recoils, creating ionization and scintillation. Ionization means electrons are knocked free from atoms. Scintillation means ultraviolet photons are produced. Arrays of sensitive photomultiplier tubes surround the xenon volume, detecting the scintillation light. Electrodes apply an electric field that drifts the ionization electrons to sensors, providing a secondary signal. By comparing the scintillation signal to the ionization signal, physicists can distinguish different types of interactions. A WIMP collision recoils a nucleus, which creates a different ratio of scintillation to ionization than an electron recoil from background radiation. This dual signal approach helps reject backgrounds. The position of the interaction also matters. Events near the edges of the detector volume might be caused by background radiation from outside, photons or particles sneaking through the shielding. Events deep in the center, in what's called the fiducial volume, are more likely to be genuine WIMP candidates. So physicists define a target volume in the center and ignore edge events. The largest liquid xenon experiment currently running is XENONT in Italy, with about 8 tons of liquid xenon. Its predecessor, XENON1T, operated from 2016 to 2018 with about 3 tons. Lux Zeppelin, called LZ, operates in South Dakota with about 10 tons of xenon, making it the largest dark matter detector ever built. These experiments are technological marvels. They achieve background rates of only a few events per year in the entire detector volume. They're sensitive enough to detect neutrinos from the sun, particles so weakly interacting that trillions pass through Earth every second, with almost none interacting. Detecting solar neutrinos is an impressive achievement, but it's also a challenge for dark matter searches because neutrinos become a background that can't be shielded. Cryogenic detectors take a different approach. These use crystals of germanium or silicon cooled to millikelvin temperatures, just a few thousandths of a degree above absolute zero. At these extreme temperatures, the crystals have almost no thermal vibrations. When a particle strikes a nucleus in the crystal, the recoiling nucleus deposits energy, creating phonons, which are quantized vibrations in the crystal lattice. By measuring these phonons with extraordinary precision, physicists can detect nuclear recoils from WIMP collisions. The cryogenic dark matter search, known as super CDMS, uses this technique. Maintaining millikelvin temperatures requires complex refrigeration systems using liquid helium and dilution refrigerators. But the sensitivity achieved justifies the complexity. Other experiments use different target materials. Dark side uses liquid argon, DEAP, the dark matter experiment using argon, pulse-shaped discrimination, also uses argon. PICO uses superheated liquids, substances held at temperatures and pressures just below the boiling point. When a particle interaction occurs, it creates a bubble which grows rapidly and can be detected optically. Different particles create bubbles with different characteristics, allowing discrimination between WIMPs and backgrounds. Each technology has advantages. Liquid xenon scales well to large masses. Cryogenic detectors have excellent energy resolution. Bubble chambers are insensitive to electromagnetic backgrounds. Physicists pursue multiple approaches, hoping one will succeed. Dozens of experiments have operated over the past 3 decades. Hundreds of physicists have dedicated their careers to the search. Billions of dollars have been invested in detectors and underground facilities. And so far, no confirmed WIMP detection. The absence of a detection is itself a result, and it tells us something important. Over the years, some experiments have reported tantalizing hints, small excesses in their data that might possibly indicate a WIMP signal. The CDMS experiment saw a few events in the early 2000s that didn't quite fit the expected background. The signals were marginal, not statistically significant enough to claim discovery. Later, more sensitive experiments saw nothing in the parameter space where those events appeared. The hints faded. The Dama experiment in Italy reported an annual modulation in their signal starting in the late 1990s. The idea behind annual modulation is clever. As Earth orbits the Sun, sometimes we're moving in the same direction as the solar system's motion through the dark matter halo, sometimes in the opposite direction. This should cause a seasonal variation in the WIMP collision rate, peaking around June, when Earth's orbital motion adds to the solar system's motion through the halo, and reaching a minimum in December when the motions subtract. Dama claimed to see this modulation. Year after year, their count rate increased in June and decreased in December with the expected period and phase. They published results spanning over 20 years, showing the same pattern, but no other experiment confirmed it. Other detectors, using different target materials but with sensitivities that should have seen the same signal if it were WIMPs, saw nothing. The WIMP properties required to explain Dama's results would have produced even larger signals in xenon-based detectors or cryogenic germanium detectors. Those signals didn't appear. Most physicists concluded Dama was seeing some systematic effect, some seasonal variation in background radiation, or detector response unrelated to dark matter. Perhaps cosmic ray flux varies seasonally due to Earth's motion. Perhaps temperature variations in the underground laboratory affect the detectors. Perhaps some other environmental factor creates the modulation, but probably not WIMPs. Dama's team disagreed. They maintained their signal was genuine. The debate continues, but the wider community remains skeptical. There have been other hints over the years. The Cogent experiment saw an excess of low-energy events. The CRESST experiment in Germany saw unexplained signals. Each time, excitement built. Each time, more sensitive experiments failed to confirm. The hints evaporated. By the early 2020s, decades of searching had ruled out the most straightforward WIMP models. If WIMPs have masses around 100 times the proton mass and interact through the weak force with the strength originally predicted, they would have been detected by now. The experiments are sensitive enough. The exposure times are long enough. They should have seen something. This doesn't disprove WIMPs entirely. It means that if WIMPs exist, they must have properties different from the simplest models. Maybe they're heavier than expected, perhaps thousands of proton masses instead of hundreds. Heavier particles collide less frequently because fewer of them exist for a given total dark matter density. Maybe they interact more weakly than expected, making collisions even rarer. Maybe they're much lighter than expected, transferring so little energy in collisions that current detectors can't register the recoils. The parameter space, the range of allowed WIMP masses and interaction strengths, has been squeezed dramatically. A large swath of possibilities has been ruled out. But the space hasn't been exhausted. Experiments continue to push into unexplored territory, building more sensitive detectors, running longer exposures, trying new techniques. Next-generation experiments are planned or under construction. Darwin, a proposed European project that would use 50 tons of liquid xenon, upgrades to existing detectors to reduce backgrounds further. New technologies that might be sensitive to lighter WIMPs. The search goes on. But the easy answers are gone. The simplest, most elegant WIMP models have been tested and not found. What remains requires either more patience, more sensitivity, or a different idea entirely. Particle physicists also searched for WIMPs in an entirely different way, by trying to create them in particle accelerators. The Large Hadron Collider, the LHC, straddles the border between France and Switzerland, buried in a circular tunnel 27 kilometers in circumference, about 100 meters underground. It's the most powerful particle accelerator ever built. Two beams of protons circulate in opposite directions, accelerated by powerful magnets and radio frequency cavities to energies of 6.5 trillion electron volts per proton, which corresponds to 99.999991% of the speed of light. When two protons collide head-on at these energies, the collision converts kinetic energy into mass, creating new particles according to Einstein's equation E equals mc squared. The more energy available, the heavier the particles that can be created. If WIMPs exist and have masses accessible at LHC energies, they should occasionally be produced in these collisions. The collision would create a WIMP and its antiparticle, which would immediately fly out of the detector without interacting with anything. Physicists wouldn't see the WIMPs directly, but they would see an imbalance in momentum. Conservation of momentum says the total momentum before a collision equals the total momentum after. In a head-on proton collision, the initial momentum in the plane perpendicular to the beam is zero because both protons are moving along the beam axis. After the collision, all the detected particles flying outward should have momenta that sum to zero when added vectorially. If some momentum is missing, if the detected particles don't add up to zero, then invisible particles must have carried momentum away. This missing transverse momentum, as it's called, is a signature of invisible particle production. The problem is that neutrinos also create missing momentum signatures. Neutrinos are standard model particles produced copiously in proton collisions. They interact so weakly they escape detectors without leaving signals. They're invisible. So every time you see missing momentum, you have to ask, is this neutrinos or something new? Physicists at the LHC developed sophisticated analysis techniques to distinguish WIMP production from neutrino production based on the patterns of other particles produced in the collision, on energy distributions, on statistical properties. They searched the data from trillions of collisions, looking for excesses above standard model predictions. They found nothing, no evidence of WIMP production, no dark matter signature. The LHC has ruled out large regions of WIMP parameter space, particularly for lower mass WIMPs that should have been produced copiously if they existed. Combined with the null results from direct detection experiments, this squeeze from two independent directions has been frustrating for WIMP advocates. The LHC continues running. Upgrades are planned to increase collision rates and gather more data. Future colliders have been proposed, larger and more energetic. But the null results accumulate. This has led some physicists to reconsider. Maybe WIMPs aren't the answer. Maybe dark matter is something else entirely. The WIMP hypothesis was never guaranteed to be correct. It was just the most popular, most elegant idea. Its failure to be confirmed doesn't mean dark matter doesn't exist. It means we need to look elsewhere. Let's take a breath and reconsider where we are. We know dark matter exists. The evidence from galaxy rotation curves, from cluster dynamics, from gravitational lensing, from the cosmic microwave background, from large-scale structure formation, all of it points consistently to the same conclusion. The universe contains about 5 times more dark matter than ordinary matter. This is solid. We know dark matter can't be ordinary atoms. Big Bang nucleosynthesis rules that out. Dark matter must be non-baryonic, something outside the periodic table. We thought WIMPs were the answer. They seemed perfect. They emerged naturally from theoretical extensions to the standard model. They had the right properties. Their predicted abundance matched observations. Everything fit, but we can't find them. Decades of searching in underground detectors have found nothing definitive. The LHC hasn't created them. The simplest WIMP models are ruled out. So what now? One possibility is that dark matter is still particles but not WIMPs. Maybe it's axions. Maybe it's sterile neutrinos. Maybe it's something even more exotic that nobody has thought of yet. Axions are hypothetical particles proposed in the 1970s to solve a completely different problem in quantum chromodynamics, the theory of the strong nuclear force. They would be extremely light, billions of times lighter than an electron, and interact extraordinarily weakly with ordinary matter. If they exist, they might be dark matter. Because axions are so light and weakly interacting, detecting them requires entirely different techniques than WIMP searches. Axion experiments use strong magnetic fields and sensitive microwave cavities. The idea is that in a strong magnetic field, axions can occasionally convert into photons. By tuning the cavity to resonate at the frequency corresponding to the axion mass, you amplify this conversion and detect the photons. Several experiments are searching for axions. The Axion Dark Matter experiment, called ADMX, operates at the University of Washington. It's scanning different frequency ranges, looking for the telltale signal of axion conversion. So far, nothing. But axions could exist across a huge range of possible masses, and the search is slow, methodically scanning through frequency space. Sterile neutrinos are another candidate. Ordinary neutrinos come in 3 types, or flavors: electron neutrinos, muon neutrinos, and tau neutrinos. They interact through the weak nuclear force, though very weakly. A sterile neutrino would be a hypothetical 4th type that doesn't even interact through the weak force. It would feel only gravity. If sterile neutrinos exist and have the right mass, they could be dark matter. Some X-ray observations of galaxy clusters have shown mysterious emission lines at energies around 3.5 kilo-electron volts that don't match any known atomic transition. One explanation is that these lines come from sterile neutrinos decaying and producing X-ray photons. The evidence is controversial and not universally accepted, but it's intriguing enough that people are paying attention. Primordial black holes are yet another possibility. These would be black holes formed in the early universe, not from collapsing stars, but from density fluctuations in the first moments after the Big Bang. If conditions were right, regions of slightly higher density could have collapsed directly into black holes, while the universe was still extremely dense. Primordial black holes could range in mass from tiny, far smaller than an atom, to thousands of solar masses. If they exist in the right mass range and sufficient abundance, they could be dark matter. They would be invisible, except for their gravitational effects, which is exactly what we observe. Recent detections of gravitational waves from merging black holes have renewed interest in primordial black holes. Some of the black holes detected by LIGO and Virgo have masses that don't quite fit stellar evolution models. They might be primordial, or they might be ordinary stellar black holes with slightly unusual properties. The debate continues. There are constraints on primordial black holes from multiple observations. If too many existed, they would produce detectable effects through gravitational microlensing, through disrupting stars and galaxies, through affecting the cosmic microwave background. Current observations suggest primordial black holes can account for at most a fraction of dark matter, not all of it. The possibilities multiply. Self-interacting dark matter, where dark matter particles interact with each other through some unknown force, but still don't interact with ordinary matter. Fuzzy dark matter, where dark matter is extremely light particles that behave quantum mechanically even on galactic scales. Dark photons, dark sectors, with whole families of dark particles analogous to the Standard Model. Each idea requires different experimental searches. Each fits some observations better than others. The parameter space is vast, the possibilities numerous. And then there's the other option, the radical option, the one that doesn't add new particles but instead changes the rules. What if there is no dark matter? What if gravity itself works differently than we think? This idea is called modified Newtonian dynamics, or MOND for short. It was proposed in 1983 by Mordechai Milgrom, an Israeli physicist working at the Weizmann Institute of Science. Milgrom looked at the galaxy rotation curve problem from a different angle. Instead of adding invisible matter to make the observations fit existing gravity laws, he asked, what if we modify the laws of gravity to fit the observations without adding anything? Newton's law of gravity works beautifully in the solar system. It describes planetary orbits with extraordinary precision. Einstein's general relativity refines Newton's law, adding corrections that matter near massive objects or at high speeds, but for most purposes, Newton's law is accurate enough. But all these tests occur in regions of relatively strong gravity. What if gravity behaves differently when it becomes extremely weak? Milgrom proposed that below a certain threshold of gravitational acceleration, gravity doesn't fall off as quickly as Newton predicted. Instead of declining with the square of distance, it declines more slowly, approaching a linear decline. This modification would affect only the outer regions of galaxies, where gravitational acceleration is extremely weak, leaving solar system tests unaffected. The threshold acceleration, which Milgrom called A0, would be extraordinarily small, about 1.2 times 10 to the minus 10 meters per second squared. To put that in perspective, Earth's surface gravity is about 9.8 meters per second squared. The Moon's surface gravity is about 1.6 meters per second squared. Milgrom's threshold is 10 billion times weaker than Earth's gravity. You would never notice this modification in everyday life, or even in orbit around Earth. The effects only become significant in the extremely weak gravity fields found in the outer reaches of galaxies, tens of thousands of light years from galactic centers. And remarkably, with this simple modification, galaxy rotation curves come out flat. You don't need dark matter. The visible stars and gas provide enough gravity once you account for the modified behavior at low accelerations. The mass you see is the mass that's there. Nothing hidden, nothing invisible, just gravity working slightly differently than Newton described. Milgrom's proposal was radical. It challenged one of the most fundamental laws in physics, a law tested countless times in countless ways. Physicists generally prefer adding new particles to changing fundamental laws. New particles are conceptually easier. They fit within existing frameworks. Modifying gravity means rewriting the foundations, reconsidering everything. But MOND had appeal. It was simple, requiring only one new constant of nature, the threshold acceleration, A0. It was economical, explaining observations without inventing new types of matter. And it made successful predictions. Mond correctly predicted the relationship between a galaxy's visible mass and its rotation velocity before that relationship was thoroughly observed. The Tully-Fisher relation, as it's called, shows that a spiral galaxy's total luminosity, which traces its stellar mass, correlates tightly with its rotation velocity raised to a power. Brighter galaxies rotate faster. This relationship is observed to be remarkably tight, with little scatter. Mond predicts this relation naturally from its modified gravity law. Dark matter models can explain it too, but they require additional assumptions about how dark matter and ordinary matter are distributed together and about the efficiency of star formation. Mond gets it for free, directly from the modified dynamics. Milgram also predicted the form of the Tully-Fisher relation, the specific exponent relating luminosity to velocity. His prediction, made before high-quality data existed, matched subsequent observations well. Mond explained peculiarities in the rotation curves of individual galaxies. Some galaxies show bumps and wiggles in their rotation curves that correspond to features in the visible matter distribution. Mond predicted these features should appear because gravity is directly tied to visible mass. Dark matter models struggle to explain these correlations without fine-tuning how dark and ordinary matter distributions track each other. For these reasons, Mond attracted a small but dedicated following. Milgram continued developing the theory, and others joined the effort. They applied Mond to different types of galaxies, to galaxy mergers, to various observed phenomena. In many cases, Mond worked surprisingly well, but Mond also had problems. Serious problems that prevented it from becoming widely accepted. The first major problem for Mond is galaxy clusters. Zwicky's original 1933 observation that started the whole dark matter story involved the Coma cluster. Galaxies in the cluster were moving too fast to be held by visible matter alone. Milgram's Mond reduces the discrepancy because the weak gravitational field in clusters falls into the regime where the modification applies, but it doesn't eliminate the discrepancy. Even with Mond's modified gravity, galaxy clusters require about twice as much mass as we can see. The missing mass factor drops from about 400 in Newtonian gravity to about 2 in Mond. That's an improvement, but it's not enough. You still need something invisible. Mond reduces the dark matter problem in clusters, but doesn't solve it. Mond advocates responded by suggesting clusters might contain substantial amounts of ordinary matter that doesn't shine. Hot gas, perhaps, or dim stars, or planets. But observations of hot gas in clusters using X-ray telescopes show there's not enough to account for the missing mass. The gas is there and it glows in X-rays, so we can measure its mass. It's not sufficient. So even in Mond, you still need some dark matter in clusters. This undermines one of Mond's key appeals, which was eliminating the need for invisible matter entirely. The second major problem is gravitational lensing, especially in colliding galaxy clusters. When two galaxy clusters collide, different components interact differently. The galaxies themselves, being mostly empty space with stars widely separated, pass through each other like ghosts. Individual galaxies rarely collide during cluster mergers. The hot gas between galaxies, on the other hand, collides violently. Gas from one cluster runs into gas from the other cluster, compresses, heats up, and slows down. The gas ends up concentrated near the collision site. In a dark matter model, the dark matter halos, being collisionless, pass through each other just like the galaxies. Dark matter doesn't interact with itself or with ordinary matter except through gravity, so the dark matter halos keep moving, separating from the gas that slowed down in the collision. This prediction was spectacularly confirmed by observations of the Bullet cluster in 2006. The Bullet cluster is actually two galaxy clusters that collided about 150 million years ago. The collision was violent and offset like a glancing blow. Most of the visible matter, mainly hot gas glowing in X-rays, ended up concentrated in two regions near the center where the collision occurred. But gravitational lensing measurements showed that most of the mass is not where the visible matter is. It's in two separate clumps on either side, exactly where the dark matter halos would be if they passed through the collision. The offset between visible matter and gravitational mass is stark and unambiguous. You can see it directly in the images. The X-ray bright gas is in one place. The gravitational lensing contours, mapping where the mass actually is, are in different places. The mass follows the galaxies, not the gas, just as dark matter predicts. Mond has no good explanation for this. In Mond, gravity is produced by visible matter. Where the visible matter goes, gravity should follow. You can't have gravity separate from the matter creating it. The bullet cluster shows gravity separated from most of the visible matter. This is strong evidence that gravity comes from something invisible, from dark matter particles that pass through the collision. There are other colliding clusters showing similar offsets. Abel 3827, Max J0025. Each one shows the same pattern. Visible matter piled up in the collision region, gravitational mass offset to where dark matter halos would be. Mond struggles with these observations. Some Mond advocates have proposed adding a small amount of neutrinos or other particles to carry mass through the collision. But this feels like adding dark matter by another name. The third major problem is the cosmic microwave background. The CMB, the faint microwave radiation left over from the early universe, contains a wealth of information about cosmological parameters. The temperature variations across the sky, tiny fluctuations of a few parts in 100,000, encode details about the density of ordinary matter, dark matter, and dark energy, about the expansion rate of the universe, about the geometry of space. By analyzing the statistical properties of these temperature fluctuations, cosmologists can measure these parameters with remarkable precision. The pattern of fluctuations depends sensitively on the densities of different components, because different components affect how density perturbations grow and how photons scatter in the early universe. The observations, made with exquisite precision by satellites like WebMap and Planck, match theoretical predictions beautifully when you include dark matter. The sizes and amplitudes of hotspots and cold spots, the patterns in the power spectrum, all fit a model with about 5% ordinary matter, 27% dark matter, and 68% dark energy. But the predictions don't match if you use Mond instead of dark matter. The pattern of fluctuations comes out wrong. The peaks in the power spectrum are at the wrong scales with wrong amplitudes. You can try to modify Mond to fit the CMB, adding extra components or changing assumptions. But the modifications become increasingly contrived. You lose the simplicity that made Mond appealing in the first place. Dark matter, on the other hand, fits the CMB naturally. The same dark matter that explains galaxy rotation curves, that explains large-scale structure, also explains the CMB, one component consistently explaining multiple independent observations across vastly different scales. For these reasons, most physicists favor dark matter over Mond. Dark matter makes successful predictions across many different phenomena. Mond works well for individual galaxies, but struggles with clusters, with colliding clusters. With the CMB, it solves some problems but creates others. That said, Mond hasn't disappeared. Some physicists continue exploring it, developing more sophisticated versions that might address the problems. Tensor vector scalar gravity, or TeVeS, is a relativistic version of Mond that incorporates Mond's ideas into a framework compatible with general relativity. It attempts to explain gravitational lensing and other relativistic effects. Other variants introduce new fields or particles that arise from modified gravity rather than being fundamental. These approaches blur the line between modified gravity and dark matter. They're trying to capture Mond's successes while addressing its failures, but in doing so, they often end up reinventing something that looks a lot like dark matter. The debate continues, though the majority view strongly favors dark matter. Mond serves a useful purpose, reminding us to question assumptions, to consider alternatives, to remain open to the possibility that our understanding might be incomplete in unexpected ways. But based on current evidence, dark matter, as actual matter, not modified gravity, is the explanation that works best. Let me share something important about how science works, something that might help make sense of this situation. Science is not a collection of facts etched in stone. It's a process of building models, testing those models against observations, refining or discarding them based on what we learn. Models are always provisional, always subject to revision. They're the best explanations we have given current evidence, but they're not truth with a capital T. They're tools for understanding, and tools get replaced when better ones come along. Newton's gravity was the best model for centuries. It explained planetary orbits, tides, the motion of projectiles, falling objects, everything we could measure. The predictions matched observations to within measurement error. It seemed complete, final, perfect. But as observations improved, tiny discrepancies appeared. Mercury's orbit showed a small anomaly called perihelion precession. The point of closest approach to the Sun, the perihelion, rotated slowly around the Sun at a rate slightly faster than Newtonian gravity predicted. The discrepancy was small, only 43 arcseconds per century, but it was real and unexplained. Starlight, passing near the Sun during a solar eclipse, bent by slightly more than Newton predicted. Clocks at different altitudes ticked at different rates. These effects were subtle, but they couldn't be explained within Newton's framework. Albert Einstein developed general relativity to address these problems. In general relativity, gravity isn't a force pulling objects together. It's the curvature of space-time itself. Mass and energy warp the fabric of space and time, and objects move along the straightest possible paths through this warped geometry. This completely different conceptual framework made predictions that matched Newton's in most situations, but diverged in specific cases. General relativity predicted Mercury's perihelion precession exactly. It predicted light bending near massive objects, an effect dramatically confirmed during the 1919 solar eclipse. It predicted gravitational time dilation, confirmed by atomic clocks at different altitudes. It predicted gravitational waves, ripples in space-time itself, confirmed by LIGO in 2015, exactly a century after Einstein's prediction. General relativity didn't make Newton wrong. Newton's model still works perfectly fine for most purposes. We still use Newtonian gravity to launch satellites, to navigate spacecraft, to calculate tides, but Einstein's model is more accurate, more complete. It works in situations where Newton's breaks down. Now we're facing similar discrepancies. General relativity predicts how galaxies should rotate based on visible matter. The observations don't match. We have the same two options Newton's successors faced: modify the model or add something new. Most physicists favor adding dark matter because it works better across multiple independent observations. But we remain open to the possibility that gravity needs modification, that general relativity is incomplete, that a deeper theory might emerge. This is how science progresses. Observations reveal discrepancies. Scientists propose explanations. Experiments and observations test those explanations. Some explanations succeed, some fail, and our understanding deepens. Confusion and uncertainty aren't signs of failure. They're signs we're working at the edge of knowledge, pushing into territory we've never explored. This is exciting. This is where discoveries happen. And eventually, we'll figure it out. Maybe we'll detect dark matter particles and the mystery will be solved. Maybe we'll discover that gravity needs modification at certain scales and develop a deeper theory. Maybe we'll find something completely unexpected that nobody has thought of yet. But we'll learn. That's what science does. It solves problems, layer by layer, mystery by mystery. Sometimes it takes decades or centuries, but the process works. In the meantime, we live with uncertainty. And that's not just okay, it's wonderful. A universe we fully understood, where every question had an answer, where no mysteries remained, would be boring. The existence of dark matter, the fact that we don't fully understand what makes up most of the universe, means reality is richer and stranger than our current theories capture. That's a gift, not a problem. Let me take you deeper into what dark matter means for the structure of the universe, for how galaxies form, for why we exist. In the standard cosmological model, called lambda CDM, where lambda represents dark energy and CDM stands for cold, dark matter, structure formation proceeds through gravitational collapse of dark matter fluctuations. In the very early universe, moments after the Big Bang, quantum fluctuations during a period called inflation created tiny density variations. Some regions were slightly denser than average, others slightly less dense. These variations were minuscule, differences of only a few parts in 100,000. As the universe expanded and cooled, these tiny overdensities began to grow through gravity. Denser regions had slightly stronger gravity, attracting nearby matter. As matter fell inward, the region became denser still, strengthening gravity further. This runaway process, gravitational collapse, amplified tiny initial fluctuations into larger and larger structures. But this process works differently for dark matter than for ordinary matter. Ordinary matter in the early universe was coupled to radiation, photons scattered constantly off electrons and protons in the hot plasma. This radiation pressure resisted gravitational collapse. When a region of ordinary matter tried to collapse under its own gravity, radiation pressure pushed back, creating oscillations, sound waves traveling through the cosmic plasma. These oscillations prevented ordinary matter from collapsing efficiently. Dark matter, on the other hand, doesn't couple to radiation. It doesn't scatter photons. It doesn't feel radiation pressure. Dark matter could begin collapsing immediately, unimpeded by any force except gravity. This means dark matter began forming structures much earlier than ordinary matter could. Dark matter density fluctuations collapsed into halos, gravitationally bound clumps. These halos grew through mergers, smaller halos combining into larger ones. A hierarchy of structure emerged, with smaller halos merging to form larger halos, which merged to form still larger halos, in a process called hierarchical structure formation. Ordinary matter, meanwhile, remained coupled to radiation until about 380,000 years after the Big Bang. At that moment, called recombination, the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. Suddenly, photons could travel freely without scattering. The cosmic microwave background we observe today is light from that moment, the last time photons scattered, before streaming freely through space. After recombination, ordinary matter was no longer supported by radiation pressure. It could finally collapse. And it collapsed into the gravitational wells created by dark matter halos. Gas fell into the dark matter potential wells, compressed, heated, and eventually formed the first stars. Without dark matter, this process would have taken much longer. Ordinary matter alone doesn't clump efficiently enough in the early universe. The first stars might not have formed until billions of years after the Big Bang, perhaps so late that the universe's accelerating expansion would have dispersed matter too much for stars to form at all. Dark matter enabled structure formation on a timescale that allowed stars, galaxies, and eventually life to emerge. In a real sense, we exist because dark matter exists. Computer simulations of structure formation illustrate this beautifully. Cosmologists run massive simulations starting from initial conditions shortly after the Big Bang, with tiny density fluctuations matching those inferred from the CMB. They evolve these conditions forward in time, using gravity, following billions of dark matter particles as they collapse, merge, and form halos. The simulations produce a cosmic web, a network of filaments and sheets with vast voids in between. Dark matter halos cluster along the filaments like beads on strings. Where multiple filaments intersect, massive clusters form. The voids, depleted of matter, grow larger as material drains into the filaments and clusters. This simulated structure matches observations of the real universe remarkably well. Surveys, mapping millions of galaxies, show the same filamentary structure, the same voids, the same clustering patterns. The match is striking. It suggests we understand how structure forms, even if we don't know what dark matter is. Within individual dark matter halos, smaller subhalos orbit. These are the remnants of smaller halos that merged into the main halo, but weren't completely disrupted. Simulations predict thousands of subhalos orbiting within the Milky Way's dark matter halo. Most of these subhalos are dark, containing no stars, because the gas that fell into them was too diffuse to cool and condense efficiently. Some subhalos do contain stars, forming what we call dwarf satellite galaxies. The Milky Way has dozens of known satellites. Small galaxies like the Large and Small Magellanic Clouds, Sagittarius Dwarf, Draco, Ursa Minor, and many others. Each is presumably embedded in its own dark matter subhalo. Observations of these dwarf galaxies provide additional evidence for dark matter. Despite containing few stars, they have mass-to-light ratios far higher than the Milky Way itself. Some dwarfs have mass-to-light ratios exceeding 100, meaning they contain 100 times more mass than their starlight suggests. This mass must be dark matter. The motions of stars in dwarf galaxies confirm this. Even with so few stars, you can measure velocity dispersions, the range of speeds at which stars move. Higher dispersions indicate stronger gravity holding the stars in the galaxy. The dispersions in dwarf galaxies are higher than visible matter alone could produce. Dark matter dominates these systems even more thoroughly than it dominates large galaxies. Let's talk about what dark matter means for the far future of the universe. Billions and trillions of years from now, current observations show the universe's expansion is accelerating. Distant galaxies are receding faster than they would if expansion were merely coasting. Something is driving this acceleration, a repulsive force or negative pressure that pushes space apart. We call it dark energy, though we understand it even less than dark matter. Dark energy appears to be a property of space itself, a cosmological constant, with density that doesn't dilute as the universe expands. As space grows, more dark energy comes into existence, filling the new volume. This constant energy density produces constant acceleration. If dark energy remains constant, as current observations suggest, the universe will continue accelerating forever. Eventually, in hundreds of billions of years, all galaxies outside our local group will recede beyond the cosmic horizon, the distance beyond which light can never reach us, even given infinite time. The observable universe will shrink to encompass only the Milky Way and its nearest neighbors, bound together by gravity into a single merged galaxy. Dark matter will continue shaping this future. Local groups of galaxies, bound by their combined dark and ordinary matter, will resist the accelerating expansion. Within our local group, the Milky Way and Andromeda are already approaching each other at about 110 kilometers per second. They will collide in about 4 billion years, merging into a single large elliptical galaxy. Smaller galaxies in the group will merge as well. Eventually, all local group galaxies will combine into one structure, embedded in a single combined dark matter halo. Beyond our local group, Galaxy clusters will similarly merge internally while separating from other clusters. Each cluster will become an island universe, isolated from all others, surrounded by darkness as receding galaxies dim and redshift beyond detectability. On even longer timescales, trillions of years, stars will exhaust their fuel. Star formation will cease as gas supplies run out. The universe will dim as stars die. White dwarfs, the cooling remnants of stars like the Sun, will fade to black. Neutron stars will cool. Black holes will sit silent in the darkness. Dark matter will persist. If dark matter particles are stable, they'll remain unchanged, still orbiting in halos, still providing gravitational structure, even as ordinary matter decays or collapses into black holes. Eventually, perhaps 10 to the 100 years from now, even black holes will evaporate through Hawking radiation. Stephen Hawking showed that black holes aren't perfectly black. Quantum effects near the event horizon allow them to emit radiation and gradually lose mass. Larger black holes evaporate more slowly, but given enough time, all will vanish. After black holes evaporate, the universe will contain only a thin soup of elementary particles, photons redshifted to infinitesimal energies, neutrinos, and dark matter particles if they're stable. The temperature will approach absolute zero. Entropy will approach maximum. No structure, no complexity, no change. This is heat death, the ultimate fate of an eternally expanding, accelerating universe. Dark matter, having enabled the brief flourishing of structure and complexity during the universe's middle age, will persist as an inert component of the final emptiness. It's a bleak picture, but it's trillions of years away. For now, we live in what might be called the stelliferous era, the age of stars, when galaxies shine and planets orbit and life exists. This era is made possible by dark matter. Without it, galaxies wouldn't exist, stars wouldn't form, and we wouldn't be here to contemplate the cosmos. Let me share one more profound observation, one more piece of evidence that shapes our understanding of dark matter. In 1992, the Cosmic Background Explorer satellite, COBE, produced detailed maps of the cosmic microwave background radiation. These maps showed tiny temperature variations across the sky, hotspots and cold spots differing by only about 30 millionths of a degree. These variations, called anisotropies, are the imprints of density fluctuations in the early universe. Slightly denser regions appeared slightly hotter, because photons climbing out of those regions' gravitational wells lost energy redshifting to cooler temperatures. Wait, let me correct that. Actually, denser regions appear slightly hotter because photons in those regions had higher energies due to gravitational blue shift effects and slightly different physical conditions. The details are subtle, but the key point is that temperature variations map to density variations. The pattern of these variations encodes enormous information. The sizes of hot and cold spots depend on how far sound waves could travel in the plasma before recombination. The amplitudes depend on the densities of different components. The statistical properties depend on the geometry of space and the expansion history. After COBE, more sensitive satellites mapped the CMB in greater detail. The Wilkinson Microwave Anisotropy Probe, WMAP, operated from 2001 to 2010. The Planck satellite, operated by the European Space Agency, ran from 2009 to 2013 and achieved even higher precision. These measurements allowed cosmologists to determine cosmological parameters with remarkable accuracy. The current best fit model says the universe is 13.797 billion years old, with an uncertainty of only about 20 million years. It's spatially flat or very close to it. It contains 4.9% ordinary matter, 26.8% dark matter, and 68.3% dark energy. These numbers come from fitting theoretical predictions to the observed CMB pattern. The fit is extraordinarily good. Every feature in the CMB power spectrum, the graph showing how temperature variations depend on angular scale, matches predictions. The first acoustic peak, the second peak, the third peak, all at the right locations with the right amplitudes. And this fit requires dark matter. Without dark matter, the predicted pattern doesn't match observations. With dark matter in the amount specified, the match is excellent. This is independent evidence for dark matter from a completely different type of observation than galaxy rotation curves or cluster dynamics. The CMB comes from light emitted 380,000 years after the Big Bang, long before galaxies existed. Yet it requires dark matter in the same proportions that galaxy-scale observations require. Multiple independent lines of evidence pointing to the same conclusion is powerful. It's how we build confidence in scientific models. When rotation curves, cluster dynamics, gravitational lensing, large-scale structure, and the CMB all require dark matter in consistent amounts, it becomes very difficult to dismiss dark matter as an error or artifact. This is why most physicists are confident dark matter exists, even though we haven't detected individual particles. The evidence is overwhelming and comes from many independent sources across vastly different scales and epochs. Now let me address something you might be wondering. If we can't detect dark matter directly, if we only know it through gravitational effects, how can we be absolutely sure it's real? How do we know we're not fooling ourselves, inventing an invisible substance to explain observations we don't understand? This is a fair question. Skepticism is essential in science. We should question assumptions, demand strong evidence, consider alternatives carefully. The answer comes from the consistency and diversity of evidence. Consider an analogy. Imagine you're a detective investigating a crime. You find fingerprints at the scene. Fingerprints are strong evidence, but they could potentially be planted or contaminated. So, you look for additional evidence. You find DNA samples. They match the fingerprints. That's more convincing. You find eyewitness testimony placing the suspect at the scene. Now you have three independent types of evidence, all pointing to the same person. You find financial records showing motive. You find security camera footage from nearby. You find physical evidence linking the suspect's possessions to the scene. Each piece of evidence alone might have weaknesses or alternative explanations. But taken together, all pointing consistently to the same conclusion, they build an overwhelming case. Dark matter evidence works the same way. Galaxy rotation curves could potentially be explained by modified gravity, but then you look at galaxy clusters and find they also need dark matter, and the amount required is consistent. Then you study gravitational lensing and find it maps dark matter distributions that match what rotation curves require. Then you analyze the CMB and find it requires dark matter in consistent amounts. Then you simulate structure formation and find dark matter produces distributions matching observations. Each observation could theoretically have an alternative explanation, but explaining all of them without dark matter requires multiple different explanations, multiple different modifications to physics, multiple coincidences. Dark matter provides one explanation that works for all of them. Occam's razor, the principle that simpler explanations are generally preferable, favors dark matter. One new component, consistently explaining many diverse observations, is simpler than many different modifications, each explaining one observation. This doesn't mean dark matter is certainly correct. Science doesn't deal in certainty. It deals in levels of confidence based on evidence. And the evidence for dark matter is strong, consistent, and comes from many independent sources. We remain open to alternatives. MOND and its variants are still studied, still tested against observations. If modified gravity could explain all observations as successfully as dark matter does, it would be taken seriously. But so far, it doesn't. Dark matter works. That's why it's the leading explanation. Not because physicists are closed-minded or unwilling to consider alternatives, but because it fits observations better than alternatives do. Let me take you through what it might be like if we do detect dark matter someday. If the searches finally succeed, imagine an experiment deep underground. Let's say it's the LZ experiment in South Dakota, with its 10 tons of liquid xenon colder than the depths of space, surrounded by photomultiplier tubes and shielding, watched constantly by computers, analyzing every photon, every event. Years pass. Data accumulates. The experiment sees background events from natural radioactivity, from cosmic ray muons that penetrate the shielding, from solar neutrinos. All of these are characterized, understood, subtracted. The search continues for something different, something new. Then, on an ordinary day, the detectors register an event in the fiducial volume. A xenon nucleus recoils. The energy and position match predictions for a WIMP collision. The signature doesn't match any known background source. One event isn't enough. It could be a statistical fluctuation, a random background that happens to look like signal. The experimenters note it, add it to the dataset, and continue watching. More events appear over the following months. Slowly, rarely, but each one has similar characteristics, similar energies, similar positions deep in the detector, similar signal shapes. The statistical significance grows. 2 sigma, meaning about a 2% chance the signal is just random background. Then 3 sigma, about a 0.3% chance. Then 4 sigma. Other experiments are notified. They scrutinize their own data more carefully. Some have been running for years without claiming discovery because they didn't have enough events. But now, looking more carefully, analyzing the data with renewed focus, some of them see hints too. The annual modulation appears. The event rate increases in June when Earth's orbital motion adds to the solar system's motion through the dark matter halo. It decreases in December when the motions subtract. The modulation has the right period, the right phase, the right amplitude. Different experiments using different target materials begin seeing consistent signals. The detection rate depends on target material in exactly the way predicted by theory. Experiments using xenon see one rate. Experiments using germanium see a different rate. But the ratio matches theoretical predictions for how WIMPs should interact with different nuclei. The statistical significance crosses 5 sigma, the threshold for claiming discovery in particle physics. This corresponds to a less than 1 in 3.5 million chance that the signal is a statistical fluke. The announcement goes out. Press conferences at multiple institutions, papers submitted to physical review letters, Nature, Science, headlines worldwide. We have detected dark matter. We know what it is. A WIMP with mass of, let's say, 250 times the proton mass. Interaction cross-section of such and such value, properties that match theoretical predictions from a specific extension to the standard model. This would be one of the greatest discoveries in the history of physics. It would answer questions asked for a century. It would confirm suspicions, vindicate decades of searching, open entirely new fields of research. Physicists would immediately work to measure dark matter's properties precisely. What exactly is its mass? Its interaction strength? Does it have any other interactions beyond the weak force? Does it decay? Does it have excited states? Astrophysicists would search for dark matter signals from space. When WIMPs annihilate with each other, they produce standard model particles that might be detectable. Gamma rays from dark matter annihilation in the galactic center or in dwarf satellite galaxies. Positrons or antiprotons from annihilation in the dark matter halo. Space-based detectors would search for these signals with renewed vigor, knowing what to look for. Particle physicists would calculate exactly what parameters in the standard model extensions are required to produce a WIMP with the detected properties. Does it come from supersymmetry? From extra dimensions? From some other beyond standard model framework? The detection would constrain theoretical models dramatically. Cosmologists would update their simulations with precise knowledge of how dark matter behaves. They would refine predictions for structure formation, for galaxy evolution, for the distribution of dark matter in the universe. It would be extraordinary, a true scientific revolution. One of those moments when human understanding takes a leap forward, when a fundamental mystery dissolves into knowledge. And it might happen. The next generation of detectors is more sensitive than ever. The search continues. Patience and persistence have solved difficult problems before, or it might not happen. We might search for another century and find nothing. We might realize dark matter is fundamentally undetectable, except through gravity, that no underground experiment will ever catch it, because it doesn't interact through the weak force or any other force we can access. In that case, we would learn dark matter's properties indirectly. We would study gravitational lensing with ever greater precision, mapping dark matter distributions in galaxies and clusters. We would analyze the cosmic microwave background with future satellites, extracting more information from those ancient photons. We would run better simulations, compare them to observations, infer dark matter properties from how structure forms. This would be less satisfying than direct detection. Humans like to touch things, to hold them, to measure them directly. Knowing something only through its gravitational fingerprints feels less tangible, less real. But it would still be knowledge. We would still understand how dark matter shapes the universe, how it affects galaxy formation, what role it plays in cosmic history. We would know it's there and know how it behaves, even if we never catch individual particles. Either way, the search teaches us. We develop new technologies, new detection techniques, new analysis methods. We train new scientists. We push the boundaries of precision measurement and ultra-low background experiments. This knowledge has applications beyond dark matter, in other areas of physics, in engineering, in technology. Science is patient. The universe doesn't care about human timescales. The questions might take generations to answer. That's okay. We're part of a continuum, building knowledge piece by piece, each generation advancing a little further than the last.